All right, this is a lecture for Friday, February 12th, 2021. And what I want to do is go over a few problems here to finish out chapter 2. And I've already done, in previous lectures, I've already done some process thermodynamic calculations where we did some very simple closed systems, just piston cylinder type of calculations. And then we did some relatively simple problems with nozzles, compressors, pumps, turbines, and things like that, where we calculated heat transfer or work or enthalpy changes, things like that. Another kind of problem that you're going to come up against in thermodynamics is just straight derivation type of problems. And sometimes these are relatively easy. Sometimes these can be kind of tricky because you almost have to kind of be able to think like the person who wrote the problem to get the answer. But a lot of times, most of these problems are just kind of following your nose through the math of the calculations. And so what I wanted to do is a couple of these. Let's look at problem 239. So 239 says, show that work and heat transfer, so work rate and heat transfer rate for an arbitrary, mechanically reversible, non-flow process are given by the following equations. And I've written the work equation down here for you. Work is equal to the integral of VdP minus delta P V. And so let's do this, and then we'll work on the heat part of the calculation. So this is reversible. This is non-flow. And what else did they say? And it's arbitrary, right? So it just means it can be anything that we want. We want to show that work is equal to integral of VdP minus delta PV. So what do we do? What do we do? Well, where can we start? So we know that work for a reversible process is equal to what? It's equal to minus the integral of PdV. And so the question is, how do I get from here up to here? And we will do in just a minute, we can do some problems. A lot of times these kind of problems, we are given some relationship for pressure. And that's usually an equation of state. For example, we're given a relationship, PV is equal to RT. All right, so P is equal to RT over V. We substitute this in, and we can integrate and solve. But we're not told what the equation of state is for this fluid. We're told it's an arbitrary. I should say it's right. Let's go ahead and write this down just so we keep it in mind. It's an arbitrary process. So that means all that we know is reversible, it's non-flow, it's arbitrary. This could be a liquid, this could be an ideal gas, this could be a van der Waals gas, this could be, whatever kind of fluid it is. So we can't really do anything with that. So what are we left with? Well, this is where the book expects you to think back to your Calc 1 or Calc 2 course and take a look at this term and see what we can do with it. And if you remember back, we had a relationship where, and this is how it was in my calculus book many years ago, UdV is equal to integral of UdV is equal to what? And this was integration by parts. Because in this example here, we have no idea what pressure is. We have no idea what volume is. And so let's see, so these are just arbitrary variables basically. And so let's see what we get. So integration by parts says that the integral of U times dV is equal to U, write this a little clearer, U times V minus the integral of V times du. That might get us somewhere. All right, that might get us somewhere. So let's see what we can do. So let's take work is equal to minus the integral of P dV. If we apply our integration by parts, what do we get? We get, let's write our little key here. U is equal to P, and lowercase v is equal to volume. All right, so this is U, and this is V. So this will be P times V. All right, and since we're integrating, haven't put the minus sign. We'll put that in just a minute. All right, so that's P times V minus the integral of V du is dP. And we are integrating this between states 1 and state 2. All right, so I'm just gonna write that. We're integrating between state 1 and state 2. And so this value, this UV, this PV, is the difference of the product of PV between state 1 and state 2. All right, and then this is the difference between, and you can see here, this is probably what we want. This is between state 1 and state 2, and then I'm going to put my big bracket around everything for a minus sign, and so this is what I get. So if I simplify this, minus of a minus, so this is going to be the integral of V dP, which is nice, that's exactly what we have. And then this is going to be minus, and this is P2 V2 minus P1 V1, or delta PV. So that's this, that's a solution here. So all this was recognizing that since these are arbitrary functions, we can just use our integration, thinking back to our calculus, we can just use our integration by parts, and we can get this answer. All right, so now the second part of the problem says, again, for this reversible on-flow arbitrary process, show that Q is equal to delta H minus the integral of V dP. All right. So where do we go from here? Well, we know that this is reversible. I'm going to write this again. This is non-flow. What does that mean? That means it's a closed system. And it's arbitrary. So in our terminology here, in our little world here, arbitrary just means that we don't have an equation of state for V and P. Where can we go? So if we think about this, if we have, let's just go back to what we talked about in chapter 2. What's the overall energy balance for a closed system? Energy balance for a closed system is du is equal to dq plus dw. All right. If we write that in, if we integrate that, we get delta u is equal to q plus w. So and this is where, you just have to kind of get used to doing these kinds of problems. Now I've got q. Right? Now I've got Q. What about W? Well, I just solved for W. So this is Q plus, now W is the integral of V dP minus delta PV, and that's delta U. All right. And if I look here, now I look back at what I want to, where I want to get to. I've got a delta H here, right? And I've got a delta U here. So what this should do is this should trigger a little thought in your mind that remembers that H is equal to U plus PV. This is a definition of enthalpy. And so delta H is equal to delta U plus delta PV. All right. And so what I can do then, so delta U is equal to delta H minus delta PV. So if I go to this equation here and I rewrite this, so delta U is equal to delta H minus delta PV, and that is equal to Q plus the integral of VDP minus delta PV. All right. So what do we have here? We've got, so the delta PVs are going to cancel, right? And we're left with Q is equal to delta H, and then we're gonna move this to the other side, so that's minus VDP, and that's our answer. So these kinds of problems are, sometimes I think they're a little tricky, and sometimes I think sometimes I question the value of them, but you know, overall I think it's good to be able to work with the equations like this. What this does is it forces you to remember some of the basic fundamental relations that we have in this course. Going from here to here, it forces you to recall that the reversible work is equal to minus PDV. And then what it does is it forces you to think back to your calculus course. And, you know, back when you were doing Calc 1 or Calc 2 in integration by parts, you probably had absolutely no practical problems in how integration by parts was used. But, you know, here in thermodynamics, this isn't totally practical, but it's maybe a little bit more practical than just using little lowercase v's and u's to get an answer. And so, you know, at least you can calculate the work that's required for any reversible non-flow arbitrary process. Of course, granted, there's no such thing as a totally reversible process, but if we had an efficiency, then we could calculate real works. And then here, we just use this relationship. So this is an example where we kind of have to know the order to do things to make it a little easier. But we recognize that this is a non-flow or a closed system. So let's think about the equations that we have for a closed system. Well, we've got the energy balance. Energy balance has Q in it. Delta U is equal to Q plus W. Well, we just solved for W, so let's plug that in. And then we get something like this where we have a delta U. So what do? Well, we remember that we want to get to delta H, so we remember our relationship between H and U, and we plug that in, and then we just do some simplification and we get our answer. So that is an example of kind of a derivation problem from chapter 2. We're going to do a few more of these derivation problems as we go through the course. We're going to do more for chapter 3, and then I think we're going to do a lot, if I remember correctly. We're going to do a lot more of them from chapter 6. So make sure that you're able to do basic integrations. Remember your integration by parts. Remember some simple integrals and things like that. All right. Problem number, let's do 2.34. Problem 234. This problem says, find an equation of work for the work of reversible isothermal compression of 1 mole of gas in a piston cylinder assembly if the molar volume of a gas is given by this equation, V equals RT over P plus B, where B and R are constants. So this is a piston cylinder device. I'm not going to draw a piston cylinder device here. This is a derivation problem. Most derivation problems, I'm not going to be looking for schematics. If you want to draw a schematic, that's fine. But what we have here is, what do we want to find? We want to find the expression for work, and I'm going to put reversible. This is a reversible process. This is for 1 mole of a gas. And what is it undergoing? It's undergoing an isothermal compression and we don't know the initial state, we don't know the final state. We're just told it's an isothermal compression. What does isothermal mean? So this is where it helps if you've done a lot of reading, or maybe some, if you're like me. I did not take any foreign languages in high school, other than I took Latin, and it wasn't at a Catholic high school. This was at a Baptist high school, believe it or not. But they offered either French or Latin, and I didn't like taking French, and so I took Latin and Greek. And so we learned all these root words and things like that. And so isothermal means constant temperature. This is one of these engineering phrases that you need to know. Isothermal, isentropic, and things like that we're going to talk a lot about. But it's a compression. And we're given is an equation of state. The equation of state for this gas is RT over P plus B, where R and B are constants. And as you can imagine, R is probably the ideal gas constant. B is just some arbitrary constant. And this is going to have units of molar volume. This is going to have units of molar volume. So we want to find the reversible work. And so what do we need to do? We need to think about what's the basic equation for reversible work of a process. Well, that's reversible work is equal to the integral minus the integral of P dV. All right. So how do we deal with this? Well, what we need to do is we need to take this is our equation of state. We need to somehow get it into this equation right here so that we can evaluate the integral. We are given, our equation of state is given to us in terms of volume. And so what we're going to have to do is we're going to have to take our equation of state and rearrange it. All right. And so we have, what we can do is let's solve this for this equation of state for P. So we have V minus B is equal to RT over P. All right. And so if we flip everything, we're left with, if we flip everything, we get P is equal to RT over V minus B. All right. And so what we can do then, let me just start up here. What we can do then is we can say, okay, the reversible work is equal to minus the integral of RT over V minus B dV. And we know that R and T are constants. B is a constant as well, but we can't just pull B out. And so this is minus RT times the integral of 1 over V minus B dV. And so you guys can integrate this. You guys can integrate this. If you need to, you can also use a table of integrals. Since all our assignments are pretty much going to be take home, you can use a table of integrals. This would also be something you can probably put into MathCAD and have it integrate symbolically or numerically if you have a definite integral. But this is going to be minus RT times the natural log of V minus B, where this will be V2 minus B over V1 minus B. And so we'll just say V1 to V2 here. Give it some a definite make it a definite integral. All right, so that is the answer to that. Did we do it correctly? Let's think about this. So this is a compression. This is a compression, so that means that V2 is going to be less than V1, right? It means V2 is going to be less than V1. So V2 minus, excuse me, V2 minus B over V1 minus B. And then we take the natural log. So I'll just write this again. This is going to be less than 1, so the natural log is going to be negative, right? So that is negative. So this is negative. This whole term is negative. And then R and T, those are positive, and this is negative. And so work reversible has to be positive, right? And this is a compression. Compression is where we are doing work on the system, and that checks. So that's a way that you can check this particular kind of problem. If you have any questions on these problems, just enter them into the discussion, into the comments in the discussion, and I will get back to them. I'd like to do one more problem, and I'm not going to test you on this stuff right now, but I'm going to do this because we're going to cover this more in Chapter 3, and so this is kind of a preview for Chapter 3. So this problem is problem, is it 235? No, sorry, it's 225. 225. It says gas is bled from a tank. Neglecting heat transfer between the gas and the tank, show that the mass and energy balances produce the differential equation. So you've got gas bleeding from a tank. If you want to think of a little schematic, this basically means we have a valve, and either it's leaking by accident or we slowly open the valve, and we've got gas coming out of the out of the valve. We want to show that, for some reason, we want to show that du is equal to h. Now your book uses h prime. I do not like using primes here because prime usually denotes to me that it's a first derivative, just from my days of calculus, and I don't like you doing that. So I'm gonna say it H out. This is an enthalpy of our outlet stream minus the internal energy is equal to dm over m. This is what we want to show. All right, and what do these things mean? Well, U is the internal energy of gas in the tank, and M is the mass of gas in the tank. H, I've already told you what H out is the enthalpy of gas leaving the tank. So that's what H out is. And I'm also going to write m dot out is the mass flow rate of gas leaving the tank. So I'll put a H out and an m dot out up here if you want to have a schematic. All right, what else are we told? We are told we can neglect heat transfer between the tank walls and the gas. So what that means is that our system, our control volume does not include the tank walls. So I'm trying to draw that up here, little dots just inside the tank walls. So we don't have to worry about the temperature change of the tank walls. All we are thinking about is that, is the temperature of the gas. All right, what else? Yeah, so somehow for this, they want us to come up with this equation for this system. So the change in internal energy now of the gas in the tank, right, over the outlet enthalpy minus the internal energy is equal to the change in mass of the tank divided by the mass at that time. So these are the internal energy at that time and the mass. What does this really mean? Well, what they are wanting you to do, this is, let's step back a little bit. What kind of system is this? Is this an open system or a closed system? I've drawn my system as being the contents of the gas in the tank because that's how everything is defined in my problem. Do I have mass flow in and out of my system? Yes, I do. I have mass flow out of my system. So this is an open system. Is this steady state or unsteady state? And the answer to that is something changing with time in here. And it's not very obvious if you just look at the equation here because they've done some simplification. But yeah, you should be able to look at this and say, yeah, something's changing with time. The mass is changing with time. The internal energy is changing with time because I've got gas leaving. So this is unsteady state, open system. And if I look at this equation, I think I should be thinking, if I've got an unsteady state, open system, and I've got these terms in it, I'm probably going to have to write an energy balance and a mass balance. And so that's where I would start. Remember, if you get stuck, step back, take a look, and then start writing things down. So it's, it might seem trivial, pedantic to write things like this, but organize your thoughts and step through things one at a time, starting from the very beginning. I've got an open system. It's unsteady state. I've got terms in here that they don't look a whole lot like the energy balance equations that we've dealt with, but it looks like we're going to have to do an energy balance and a mass balance. So let's do that and go on from there. Now, the thing I don't like about this book is this is an open system. It's an unsteady system. If you page through the chapter 2 text in your textbook, your book does nothing. They do nothing about unsteady state systems. The only thing they do is on the equations on page 49, 50, and 51. They give you the equations that include an accumulation term. But if you look at the example problems that they do nothing for an open system that's unsteady state. So if you're looking at this and you have no idea how this would be solved, don't feel bad, because you really shouldn't have an idea based on just the material that's in the textbook. This is one of my pet peeves of this particular textbook, but we will work through this. All right. So we do an energy balance and a mass balance. Let me write a couple more things down here. If we do an energy balance, remember, energy and mass, they have this form. Accumulation rate equals in minus out plus generation. I'm going to write a couple things here. Mass balance is going to be easy. So let me just go ahead and write that down first. What's the mass balance on our tank? Remember, it's the tank. So it's accumulation. We're going to have accumulation. So dm dt. Do I have an input term? No, I don't. I have no mass entering my system. All right. So the input is 0. But do I have an output term? Yes, I do. It's m dot out. So it's in minus out. So it's minus m dot out. And of course, mass, there's no generation. So this is my mass balance. That's easy. What about my energy? My energy balance, remember, I have accumulation and it's unsteady state, so I'm going to have that term. My ins and outs. Do I need to, maybe I should just go ahead and write this. All right, so accumulation is going to be dm times u, so this is the mass times the internal energy. So that's the total energy, because remember, our internal energy is kilojoules per kilogram or joules per gram or whatever it's a specific internal energy. So we have to multiply it by the mass at that given time. So that's our accumulation. Now we have our in and out terms. So that's going to be what? Well, we have no inlet terms, right? Energy is not coming in by any kind of mechanism in this. First of all, there's no heat transfer, right? So I'll write that. So there's no Q. Is there any work done? And remember, this work W, or I should write Q dot. What about W dot? Well, there's no W dot either, right? Because do we have any expansion contraction of our tank? No, this is not like a balloon. This is a solid walled tank that's not going to expand and contract. Do we have any shaft work? No, there's no shaft work either. We're not pushing a turbine or anything like that. All we're doing is opening a valve and it's just flowing out. So there's no Q, there's no W. What about kinetic energy and potential energy? Well, there's nothing in here about kinetic energy, so we can say that delta kinetic energy, and these are assumptions that we could have written down earlier, but I'm going over them now. Delta kinetic energy is essentially 0. Also, delta potential energy is essentially 0. All right? So that makes our energy balance a little more simple. So there's no inlet term. There's no Q dot, W dot, KE, PE. And so now we're just left with an outlet term. So it's m dot out, and it's enthalpy out. All right. So this is our mass balance. This is our energy balance. How do we go from here to here? Well, we can do some simplification, and this is really just kind of a lot of algebra. But we also have to use one calculus trick, and that is we have to use the chain rule. Or is it the, sorry, it's not the chain rule. It's a product rule, I believe is what you guys called it. So dmu dt, these are, remember, these are variables. These are changing. We don't have constant mass. We don't have constant internal, specific internal energy. These are both changing with respect to time. So this is m times du dt plus u times dm dt. And that's equal to minus m dot out. What is minus m dot out equal to? Well, here's where you can do another trick. So that's minus m dot out is equal to plus dm dt times h out. So minus, don't get confused here. This is minus m dot out minus m dot out. That's equal to plus dm dt. All right. So how we get, what can we do here? Well, we've got m times, this now it's just simplification. It's basically what we're doing is we're separating variables here. So let's see if we can do that. M times du dt. Let's move all the dm dt's over to one side. And so we're left with dm dt is times, so h out minus u. So we've moved this over to that side, factor out the dm dt, you get h out over u. That looks promising. We've got that, but how do we, what do we have here? Well, now we just need to, we're basically just separating our variables now. So we have du dt times 1 over h out minus u is equal to dm dt times 1 over m. And then we multiply through by dt, we get du over h out minus u is equal to dm over m. And this is our answer. We got what we were supposed to get. This is not the most intuitive problem. If the first time, again, like I said, the first time you look at this, you may not have any idea how to do it. Don't feel bad. We are going to do this a little bit more in chapter 3. I looked through all the problems in the back of chapter 2, and I think this is the only unsteady state problem that I saw in chapter 2. 247 is one. We can look at that later, but this is what we'll do. And what these equations, the reason why I'm going to introduce it now, and I'm not going to really test you on anything right away here in chapter 2 regarding unsteady state problems, but in chapter 3 we'll do it. The reason why I'm covering this now is just to give you a preview of what something that we'll do in chapter 3, and also that we will then be substituting terms into here so that we can calculate, for example, what's the temperature of the tank at a certain time, or something like that. So we will be plugging equation of state information in here to allow us to figure these things out, because usually you aren't really concerned with what's the internal energy of what's in the tank. You want to know what the temperature is, and by using the ideal gas law, we can then calculate if the pressures aren't too high, we can figure out that as the tank empties, what the temperature profile is. Also, your book asks a question, under what conditions can one assume that H out is equal to H? And what they mean is, what conditions can we assume that the enthalpy of the gas that's leaving is equal to the enthalpy of the gas that's in the tank? And so the answer to that is that the contents of the tank should be well mixed. That is, we don't have temperature gradients, say from the top of the tank to the outlet or anything like that. That there aren't gradients in temperature or pressure or anything like that. That the contents are well mixed. This valve here. We'll talk about this. This is basically also called a throttling valve. And we will cover this. In a throttling valve, your delta H for that process is equal to 0. And so that's basically what this is saying, is that the enthalpy of the gas that is in the tank doesn't change as it goes through the valve. The delta H is 0. All right. So those are some example problems from Chapter 2. That pretty much covers everything that I want you to know from Chapter 2, along with the homework problems. If you have any questions, again, you can enter them in the discussion section, and I will do my best to answer. If anything else comes up that is really a shortcoming, let me know if you would like to see a problem-solving session like this for other problems. But hopefully you can use this to make your way through the rest of the problems in Chapter 2.